Hello everyone. As we reach to the 18th lesson in our series of learning the maths of quantum mechanics, today we are going to explore some fascinating concepts in quantum physics, like joint quantum operations, the tensor product, and working with multiple qubits. These might sound technical, but they are very fundamental for our understanding of how quantum physics and quantum computing works at a deeper level. I will walk you through each concept step by step with examples to illustrate how qubits interact and how to build complex quantum systems. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the 18th lesson on the series of Mathematics of Quantum Physics. Before we go ahead, here is a quick recap on the earlier lesson, that means the 17th lesson, because this would be quite related to the earlier lesson. Also, you can check out the series on the Mathematics of Quantum Physics playlist where all these videos are laid out. So in the last video, what we saw is that why do we need the mathematics of quantum physics, and we came to know that the basic concept is that we are going for miniaturization. So getting things small from big requires the mathematics. So whether you know or you do not know, you are actually doing the mathematics unknowingly. We looked into what are called qubits, we looked into what are called an 2n system, and how all the possible computations can be done parallelly, and this is called parallelism. So quantum parallelism is also what we looked into, and we saw how do we use multiple quantum states using something which is called a tensor product, turning one vector into another, and definitely we are going to look more deeper into that. We also looked into the concept of composite quantum system, what are tensor products, what are the probabilities these things can be drawn, and what are the dimensions, the different dimensions that are actually driven from a composite quantum system. So the question comes that what is next? We actually started and gave a hint a little bit on the earlier lesson. So what next? So first we start with what is called joint quantum operations. But before we go ahead into the mathematics of joint quantum operations, we are going to recap a little bit on the earlier simple parts so that the understanding is better. Now we know that what is called a unitary operator, where a kind of a mathematical transformation that actually preserves the probability of a quantum system. Now if I take a unitary operator U, for example, in quantum mechanics, which is a linear operator that preserves the inner product in an Hilbert space. So here you can see this one is basically called is the adjoint of U. This I is basically called the identity matrix, and from here what we can understand is that unitary operators represent the time evolution and quantum gate operations in quantum mechanics, and they are essentially maintaining for the reversibility of quantum process. We also know what is called a qubit. It is the basic unit of a quantum information, analogous to a classical bit, but it can exist in superposition of states. So if you take this example, for example, a qubit is represented by this, where alpha and beta are basically complex numbers, and they satisfy what is called this one. So the superpositioning, actually this property enables qubits to perform quantum parallelism, which is the foundation of quantum computing, and they do much faster. Now we are going to look into tensor product, but before that, this is just to give you a hint that this cross sign with a circle, it is basically an operator which denotes what is called tensor product. So what a tensor product does is that it combines two or more quantum states into a larger composite system, forming multiple qubit system. So that is why you see that I have given the hint that it is a multi-qubit system. So the tensor product also acts as a unitary gates, describing simultaneous actions on each part of a composite system. So from here, what we can give you an example for is this one. This is basically how the tensor product happens. So we take two states and it combines into one. Now suppose we take U1 as a unitary operator and it is acting on a qubit, say for example 1, and U2 is another unitary operator which is for example acting on unit qubit 2. So when we take a tensor product, u1, you can say times u2, this must have the property of this. Now it might look a little bit weird, but let me give you an idea that what this equation actually looks like. So this u1 and u2 basically represent quantum operators which are acting on individual qubits. They actually preserve the total probability of the system, which is very much mathematically required. Now we go to this one 4, which is called the dimension. We will look into that later also. This sign is basically called the tensor product, which combines the individual operation in order to make a joint operation. Now this one psi1 and psi2, these are actually representing the joint states of the qubit system, and this 2 is basically acting on qubit 2, which is 1 and 2. So from here, let us rewrite the equation in a fresh page. So what we get is that if we apply a quantum operation of u1 and u2 to a joint state psi1 and psi2. So what it says that applying a joint quantum operator u1 times u2 to a joint state psi1 psi2 is equivalent to applying I would say the individual operators u1 and u2 to the individual states, which is psi1 and psi2 respectively, and then we combine the results using what is called the tensor product. So make things a little bit simpler, you can say the resulting joint state after applying the joint quantum operation, this must be equal or equivalent to the joint individual state after the individual operation, this and this. So what comes out very important from here is that when we apply a joint quantum operation, whatever be it, and when we apply it to a joint state psi1 and psi2, it is equivalent to applying the individual operations of u1 and u2 to the individual states psi1 and psi2. So a joint quantum operation would be something which is equivalent to applying the operations on individual states, and this is done by using what is called this cross circle, which is called the tensor product. So here is a quick summary. When you perform a joint quantum operation on a system of multiple qubits, the outcome is the same as if you have performed individual operations on each qubit separately and then you combine the results. So from here we would like to have almost an explicit representation of the operator this one, isn't it? Because now we would like to write things explicitly. So we would like to have an explicit operation using this tensor product signature so that we can have an explicit representation of two states psi1 and psi2 and operators u1 times u2. And this is which is coming up next in our video, and that is what is called a Kronecker product or the tensor product. So let us look into what is a Kronecker product into the next part of the video. So this is the definition. The Kronecker product, also referred to as, now this is actually discovered by somebody called Leopold Kronecker, and I have made a very small video, I think around 2.5 years back in Physics for Students on my channel. You can check out who was Leopold Kronecker, where I given a little bit about his life and achievements. Anyway, it is a special way to join vectors to make big vectors. Now this is a kind of a definition, but let us look into an example. So if I take these two vectors, then the Kronecker product would be defined as this. So all you can see are just we are multiplying the first vector with the second, then again the first vector with the second vector on the second matrix, and so on. And then we combine this together. This is actually how we make a tensor product. But in order to signify it, we use that circle with a cross sign. Otherwise, it will be coming as just a multiplication, and that is not. So let us look from here. What do we mean the example through a matrix? So if A is a M and N, M times N matrix, and B is a, say for example, P times Q matrix, then multiplying A by B, I mean to say taking a tensor product would look something like this, and dot 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 means it would go on like this. So this is basically the definition of a Kronecker product or a tensor product in terms of vector and matrices. It looks like this. Now we would like to show you some very simple examples. These examples will give you a better visualization and a better understanding of a Kronecker product. So the Kronecker and tensor product of the following two vectors. For example, if I take this one, it would be something like this. So v times w would be this, and finally it would look into this. Now note that it is coming as a four-dimensional vector, 2, 4, minus 3 and minus 6. And that is why you see that it is another kind of a multiplication, but we are using the rules of the tensor product. Let us see another example. So that is what I told, that it can be extended to any dimension. Say for example, now if I take a vector of this which has got 3 and with w which has got 2, this would ultimately result into this, and combining with a tensor product we get this. So what it is, this is basically a final vector which has got 1, 2, 3, 4, 5, 6. So it is a 6-dimensional vector. So from here what we can understand, that the combination of dimensions are also possible. Now let us say we take this example. In terms of qubit we state this one, and the second qubit is in state of this one, and the combined state this and this represents this one. So from here again what we say, that when we combine the two qubits 0 and 1, it is represented as this, and this is again a 4-dimensional space with a 2-qubit system. 1, 0 and 0, 1, these are 2-qubit system. But what comes out is basically what is called a 4-dimensional space. Now if you have looked into my earlier videos on this series of the mathematics of quantum physics, then you already know what is called a Hadamard matrix. And I will use an example of an Hadamard matrix here. So if we have a Hadamard gate which is H, which is acting on a qubit represented by the matrix this, and if we want to apply H to each qubit system, we use the Kronecker product, this one, and from here we get the result as this, and finally this, and we go here. So as you can see, the matrix represents the Hadamard operation on both qubits of the 2-qubit system simultaneously. So as we are applying those Hadamard matrix and earlier 2-qubit system, etc., so what we are getting is actually this one. So so the matrix represents Hadamard matrix on both qubit systems. So what we get is what is this one, which is called a multiple qubit. And in the next part of the video, I will be explaining with very simple demonstrations and examples what is a multiple qubit. Now before going into multiple qubit, again a quick recap. What is a single qubit? Well, single qubit is something which is the fundamental unit. So 0 and 1, for example, can be represented by this, which are satisfied by this one. And we know alpha and beta are complex numbers. Now multiple qubits are nothing where we have multiple qubits and their joint quantum operation is represented by this tensor product. So if we get phi and psi as two different type of states, then the joint state would look something like this. Now what is interesting is that this creates a new state that is a combination of all possible states of the individual qubits. So this is what is called a multiple qubit, and we will soon see what is the advantage of this. So let us take this one. Now here you can see that the dimensions of the joint state slowly can increase with the number of qubits, 1, 2, 3, 4 and so on. So if it increases, then obviously it can increase up to n. So if we have n qubits with the individual states starting from psi 1 and going up to psi 2, then the joint state will be given as this. Now hold on, this actually signifies 4 important I would say points which are worth noting. The first one is called that multiple qubits actually allows for creating more complex quantum states, especially for quantum physics, advanced quantum physics, quantum computing. This would be required. Also what we see is that the tensor product is used to combine the states and you create a joint state that we have seen. The dimensionality, which is very important, of the joint state grows exponentially with the number of qubits, and last but not the least, quantum entanglement, which is now being used for cryptocurrency, data security, etc., is fundamental property of multiple qubit system. Obviously, one state, when you entangle it with another, then it creates multiple qubit states, and this becomes extremely important for data security, etc. So, as I told you, the mathematics is not just on your paper or your research or doing a PhD. It is very much applicable for the benefit of of mankind. So we will take further example of this multiple qubit state one by one so that things become easy. It might sound repetitive, but remember, repetitive things actually creates a better cognition in your mind. So we take this kind of a state. What it says is that we have two qubits, both in the zero state, and this is the tensor product. So we have both qubits in the zero state. This is actually what is called the tensor product, and it is used to combine the states of multiple qubits into a joint state. In this case, remember that we are taking the tensor product with zero itself, and what we get is this one. Now here you remember the resulting four-dimensional vector represents the joint quantum state of the two qubits. Each element is in the vector corresponds to a possible outcome, and the only non-zero element, which is 1 in the first, which means that the only possible outcome is both qubits being measured in the zero state. So quick summary, tensor product is a fundamental operation in quantum mechanics. It allows us to represent joint states in a qubit as a single vector, and the dimension of the joint states increases exponentially with the number of qubits. This is important. We see the next example, which is something like this. Here we are combining 0 and 1. So we get the same thing. We have both qubits in 0, 1, 1. Here also we are using the tensor product. And here we are getting again a four-dimensional vector. So here you can see the second element again is a non-zero. Let us go to the next example. Here we are combining 1 and 0. And again we are using the tensor product. And here the resulting vector is 1. Here the third one. So the third element is 1, which means what? That the possible outcome is measuring the first qubit in the 1 state and the second qubit again in the 0 state, as because it is the third element which is non-zero. Now what if we combine both 1 and 1 together? We get the same thing. We are getting a tensor product, and here we are getting the fourth element, which means the only possible outcome is measuring both the qubits in the state 1 system. Now before going into the next part of our video demonstrating some more examples of qubit system, I would like to introduce two friends, two little cute friends, one whose name is Alice and another whose name is Bob. Now who are they? In general, what happens in quantum mechanics and in classical physics, especially in relativity, we often use these two names so that we can, I would say, attribute certain properties to either Alice or Bob. So when we use Alice and Bob, we say often that the first qubit belongs to Alice and the second qubit belongs to Bob. And since they are friendly with our qubits, we give them name Alice and Bob. So what we see here, that Alice has got a quantum state this and Bob has got a quantum state this. Then their combined state, if we combine them, they would look like this, and the output would be finally again a kind of a four-dimensional vector. Non-zero elements again are 1 and 1. Now my question to you is that first two, if they are the non-zero elements, what is the output? I mean to say, what would be the possible outcome? If you can make it out from this part of the video, please let me know in the comment box. Now we are going to introduce another friend whose name is Charlie. So we have got Alice who has got a state of this, Bob who has got a state of this, and Charlie who has got a state of which is called a chi. And when we combine Alice, Bob and Charlie state together, we get something like this, which finally results into this. So finally it comes into, so 1, 2, 3, 4, 5, 6, 7, 8. So here we get a 8-dimensional vector. What do we mean by this? Let us turn the next page and we will make a complete understanding. So here you can see it is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it is an 8-dimensional vector. So this part. So and the coefficient in the vector represents what? The probability. This part represents the probability for each outcome. So what we get is that the resulting n-dimensional vector represent again the joint quantum state of the 3 qubits. Each element of the vector corresponds to a possible outcome, obviously, and this coefficient 1 upon 2 square root of 2. So the probability of measuring all 3 qubits in the state 0 is given by this. That means the probability is 1 upon 8. And now what would 1 upon 8 mean when it comes to physical experimentation? That is a different issue, but this is theoretically and mathematically how we are getting into this. Now suppose we get something like this, okay, and we can calculate the possibility of the outcome in terms of probability. So we are using the tensor product to get this. Again we get a 4-dimensional vector, and from here we get this. Now here we will do something which is called the Bound's rule, or the squaring of the amplitude, etc., which you already know from quantum physics. So if we compute the Bound's rule, we get the result as this. Now from here I am going to take the inner product using the Kronecker product. In the next page here I am going to take the inner property of the inner product property, and by squaring Bound's rule we already got this, and final result is again 1/4. Again, what would 1/4 mean in terms of physical interpretation? That is a different issue, but this is how we mathematically and theoretically we derive it. So that's all for today's video. We are coming almost to the end of this series because we are done with a lot of lessons on quantum physics, starting from complex numbers, and now today we are going into qubit system and quantum system. So we will continue this series for a few more understanding of the videos. So I will take a pause, and I would like to thank you everybody for taking up the time to watch this video. So if you have liked it, please do subscribe and click on the bell icon to get all the notification from Physics for Students. You can write to this email ID of mine, and you can also subscribe to my other channel exclusive to General Theory of Relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue with this series as well as the other courses which I have started. Thank you very much for supporting, and see you soon. Until then, goodbye.